Okay, so can everybody hear me and see my screen? Excellent, thank you, Oliver. Okay, so we were talking about responsibilities and guidelines for identifying responsibilities. And then somebody muted me. The fourth guideline for identifying responsibilities is to re-examine candidate classes. So if you introduce a class into your design, that the mere presence of a class implies at least one responsibility. For example, a class needs to know how to instantiate itself or delete itself, right? These are important responsibilities that are usually inherent in a class, right? The name of the class may imply some responsibilities. For example, collections. Collections certainly imply responsibilities. A statement of purpose in the requirement specification may also imply responsibilities. And any attributes almost automatically imply responsibilities, especially, for example, get methods or set methods. Okay, so we've had these two phases. One is identifying objects and classes. The next one was identifying responsibilities given a requirement specification. And then the next stage is assigning responsibilities to classes. So some guidelines on assigning responsibilities to classes include examining content in which the responsibility was identified, using the requirement specification as well as class definitions. Some assignments will be obvious and others will require some thought. Right, when you are writing software, especially in a large project, you want to think about where your methods are going and if they're going in the right place. So, some guidelines include distribute system intelligence evenly. That means no classes should be too big. It's hard to define exactly what that means to be too big, but one symptom of a class that is too big is if two or more people are fighting over that class. So two or more people are trying to edit a class and need to be developing it at the same time. That's usually a sign that a class has too much intelligence. Generally speaking, one class should be assigned to one developer, or only one developer, generally speaking. Of course, there are exceptions. State responsibilities as generally as possible. Keep behavior and actions with related information, so the methods and the data that operate on those methods, the methods that operate on that data are together in the same object. Keep information about one thing in one place, right? This is, I think, something that was mentioned previously. So a boring example is the time example. There is only one time object, and that one time object is responsible for maintaining the current time, and no other objects are responsible. That's a basic principle in object-oriented design. And the reason is because if you try to have two time objects, inevitably what would happen is inconsistency, right? It's impossible to keep the same information in multiple places and keep it consistent. Well, it's not impossible, but it leads to problems, or it can lead to problems. And responsibilities can be shared. Oops. Can everybody still see my slides and hear me? I just pressed a button and I hope it wasn't the wrong button. Okay, good. So I'm using this word intelligence. Intelligence is essentially a set of responsibilities. So a collection of methods and a collection of data or member variables that those methods need in order to carry out their functions. So a system intelligence is what a system knows, the actions the system can perform, and the impact the system has on other systems. Class intelligence is determined by two major components: what services it provides, this from the server perspective, and what services it uses, the client perspective. So what information and processes does it provide to other objects, and what other objects does it need in order to carry out its own responsibilities? This is what we call class intelligence. So as we mentioned, a class can be a server or a client, right? And it's often both of those things. The server view of intelligence is what does the class itself know by itself without relying on any other objects, and what actions can it perform for other clients. The client view of intelligence is how many other classes do I need to communicate with in order to carry out my responsibilities, right? Who do I have to communicate with in order to fill my role in a greater system, right? And how much do I need to know from other server classes? Here are some examples of class intelligence. So collection objects like arrays and sets have relatively less intelligence. They have little effect on even objects stored in them, right? Arrays, for example, are essentially responsible for indexing. An application class, like a drawing editor, for example, has high intelligence. It has to know about a lot of other classes, right? And I'm often going to be referring to this hypothetical drawing editor class or a drawing editor application. What that means, a drawing editor application is a piece of software that we use to draw diagrams, right? Sometimes we need to draw diagrams for maybe UML diagrams or just other diagrams, and there are special pieces of software that do that draw figures. And I'll often be referring to this hypothetical example, drawing editor, in the slides as one of my examples. Pierre often likes to refer to the zoo and the zoo manager application. I like to refer to the drawing editor application when I'm thinking about examples of these principles and putting these principles into practice. We have also centralized intelligence. So you could theoretically have one class that contains all of the intelligence. You can put an entire application into one class, right? That's the old days. That's a process-oriented design, right? So taken to the extreme, one object can incorporate all of the system intelligence. That's centralized control or centralized intelligence. It's like having a main method with everything in the main method, right? And there is an advantage to this. The advantage to a process-oriented design is it's easier to understand the overall flow of control and information flow, right? You can start with the first line and just move down until you hit the end of main, and you understand the flow of processes, and you can understand the flow of information, not automatically, if you have only one method that contains everything in it. That's not the approach we're using here. So some of the drawbacks to that approach is that it hardwires the system behavior and makes it less adaptable to changes, so future versions. It also integrates multiple design decisions into a single class, so it makes it less likely that one implementation decision can be changed without affecting everything else, right? There's far less code sharing and code reuse and less design sharing. And of course, if you were trying to work in a team and you were all trying to edit the same class, that would be a disaster, right? That would be a real big disaster. So our design is trying to do the opposite, which is distribute the intelligence, right? And this does have a disadvantage, by the way. The disadvantage with object-oriented design is it becomes more difficult to understand the flow of the processes, the flow of control and the flow of information in your application. This is one of the drawbacks to object-oriented design. And this is one of the reasons we talk so much about this. We're drawing lots of diagrams to try to understand the flow of control inside a program and how information is passed around to each object, right? We spend a lot of time drawing different UML diagrams or other types of diagrams to try to understand this. And this is one of the things that is more complicated in object-oriented software as opposed to, say, one long process or a process-oriented application. So we want to minimize the number of intelligent classes. The goal is to have all classes equally intelligent. That's not possible, but that's a goal to aim for. Each object knows relatively little. Each class encapsulates only a few related design and implementation decisions. And one way we can look at this is to try to compare the number of responsibilities assigned to each class. Right? How many methods does your class have? How many member variables does your class have? If it gets too big, then that means intelligence is becoming too centralized and you're getting more towards a process-oriented application. If a class gets too intelligent, it's usually a sign that you need to introduce a new class or a new set of classes, right? If a class has a particularly long list of responsibilities, maybe that's a sign that your responsibilities are expressed at too low of a level of detail or in too much detail. It might make sense to introduce a new class or move some responsibilities to another class, right, if it makes sense. And it also is a sign that maybe your class needs to be subdivided. This happens in real life, by the way. I've seen it many times that a class becomes too intelligent. In other words, there are too many methods in a class and a class becomes unmanageable, right? The larger a class is, the more likely it is to turn into legacy code, and we're going to talk about that in the forthcoming weeks. So in general, we want to state responsibilities as generally as possible. So for example, instead of stating that a line element knows how to draw a line and a rectangle element knows how to draw a rectangle, we say that both know how to draw themselves. right? So if we have an object called rectangle element, it has a method called draw. And if we have a line element object, it also has a method called draw. And both of those draws have different implementations, but conceptually they're the same thing. They're the objects knowing how to draw themselves, right? A line element knowing how to draw an edge, and a rectangle element knowing how to draw a rectangle. This kind of statement of responsibilities leads to more shared responsibilities. For example, the responsibility to draw, right? That is a responsibility. And it also leads to more general classes. I'm repeating myself here as well. This is in bold font. Keep related behavior with related information. So that's the methods and the data that are related belong together in the same class. If an object maintains particular information, it should be responsible for performing any operations on that data. Right, that's pretty obvious. I think everybody knows that. Okay, this is another guideline for responsibilities, keeping information about one thing in one place. So maintenance of a specific piece of information should not be shared. This leads to duplication of information, which may lead to inconsistency. Another example of that might be a database, right? A database there should only be one instance of a database. You don't want to have multiple instances of a database duplicating information. This is a disaster, because the database will become inconsistent over time, and you also are introducing problems for memory, right? Duplicating a database is very memory inefficient, right? So this is a very general principle. If more than one object must know the information, then assign the information to one class, for example, database, or a class called time, or a class called date, right? These things have to be maintained by a single object. And could be its only responsibility, is just to maintain that information. If all the objects requiring the information have little else to do, perhaps they can be collapsed into a single object or class. Generally speaking, we create a new object that takes on the responsibility of managing the information. I think everybody can understand this principle without too much trouble. Splitting shared responsibilities, it can happen that some responsibilities need to be shared among several classes. They are compound responsibilities, right? These kinds of responsibilities can be complex, like rendering, for example, or displaying something, or drawing something, or printing something, right? These kinds of responsibilities can be very complicated, and therefore those kinds of responsibilities can be shared amongst several classes. For example, a parent and several children, or another object that has several composite objects inside of it. Right. And this is something that often might end up being something like a subsystem behavior. So it's not very difficult to imagine a drawing subsystem or a rendering subsystem for figures or graphics. It's not very hard to imagine a printing subsystem. This is kind of a forward reference to subsystems, which we'll talk about later. But when I see this guideline here, split shared responsibilities, I'm actually in the back of my mind thinking about subsystems, which I haven't really talked about in detail yet. Okay, I think I've already gone over those things. Examining class relationships. So this is something that has been mentioned already. We're going to mention it again because it's really, really important. And I'm very surprised at how often I see these class relationships going wrong, so to speak, or getting very confused. At the last job I had, which was a software development job, I was working in a team of software developers, and I was really shocked to see that many of the software developers could not make the distinction between an is kind of relationship or an is type of relationship and an is part of relationship. And this leads to disasters. This leads to design disasters. And this is something we're going to talk about right now. There may be many application-specific relationships between classes. So identifying these relationships may indicate new responsibilities. And these are the two most common relationships between classes: the is kind of relationship and the is part of relationship. The is kind of relationship is associated with inheritance. So a child is a kind of parent, right? If one class is a kind of another class, look for subclass, superclass relationships, right? Shared attributes or behavior can imply an is kind of relationship, right? An example from the drawing editor that I'll refer back to is a text creation tool, a line creation tool, are all kinds of creation tools. They share three responsibilities: accepting user input, determining the location of a new drawing element, and creating a new instance of a drawing element. All three of these responsibilities could be assigned to a parent class called creation tool and inherited by the others, right? Only the second one, however, is likely to be implemented by the superclass. Others are probably specific to the subclasses, right? The is part of relationship is associated with composition, right? One's a class hierarchy. The is kind of relationship defines a class hierarchy. The is part of relationship defines an object hierarchy or composition, right? And it's really surprising how often these two relationships get confused. At the last job I had, a lot of the developers didn't understand the is part of relationship, and they tried to model all behavior after the is kind of relationship. Right? And yeah, it's just too bad. And that project was a failing project. What do I mean by failing project? A project can be failing in many different ways, right? One of the ways that a project could be failing is that it's losing money. So the last project I was working on in industry was losing millions of euros every year, right? And part of the reason was because of the design and the lack of design and the lack of coding conventions and coding standards. Anyways, I've seen this in real life. Other developers not being able to make the distinction between the is part of and the is kind of relationships, even though they're actually really, really simple. So it is part of relationship defines an object hierarchy, not a class hierarchy. So you can think of this example. An arm is a part of the body, right? A hand is a part of the arm, and a finger is a part of the hand. That's an is part of relationship, or a composition, right? A composite, the body in this case would be called a composite object. It is composed of other objects, right? And this is also called an object hierarchy, but it's not a class hierarchy. And if you get confused, you can just say the sentence out loud, right? Imagine me saying, arm is a type of body. That sentence does not make sense, right? The arm is not a type of body. It just doesn't make any sense, right? If you just say the natural language, if you just speak it out, it will become clear. If you find yourself saying something that makes no sense, then it means you need to think more carefully about your object relationships and your class relationships. If I say, you know, a house cat is a type of cat, yes, that's fine. That sentence makes sense. If I say a house cat is a part of cat, it doesn't make sense, right? If I say a paw is a part of house cat or cat, that makes sense, right? If I say a paw is a type of cat, it makes no sense. So listen to yourselves and listen to your own natural language. In live classes, I've done quizzes where I ask a student to actually say a sentence, and sometimes they will come up with the strangest sentences that don't make any sense, right? Like, a tire is a type of car. No, a tire is a part of the car, right? You could say, you know, a Mercedes is a type of car or something like that. Anyways, keep those two relationships distinct in your mind. The is type of, is kind of, or is type of, is modeled through inheritance, which you're very familiar with, parents and children. The composite relationship is implemented as member variables, objects being a member of another object, right? And a body object containing 4 arm member variables or member objects. It's really, really simple, actually. And then unassigned responsibilities, there it can happen that after your responsibility analysis you still have unassigned responsibilities. This might imply that a class is missing. You may need a special class to put in miscellaneous responsibilities or something like this. A responsibility could be assigned to more than one class. This usually implies shared behavior, and you could lead to the introduction of new abstract classes. Sometimes you might have a responsibility and you're just not sure where it goes, and you can make an arbitrary assignment or take a guess and just see how it works, right, after you've done a walkthrough of your system. Okay, this is the first kind of tool, let's say. So if we're designing object-oriented software, if we're given a specification, one starting point is creating class cards. So that's literally something like a post-it note to start with. And on these notes, or these class cards, or I think index cards are what they're modeled after, you have this information that you write on it. You have a class name, like creation tool. It has the names of any parent classes or superclasses. Like you can see here, creation tool is a type of tool, right? It follows the is kind of or is type of relationship. There are subclasses there, like line creation tool, rectangle creation tool, and so on. And then there's a list of responsibilities there. Accepting user inputs, determining the location of the object, and creating a new instance. What's missing there is another implied responsibility, which is deleting an instance, right? Or being a tool being able to delete itself. Maybe. It depends on the requirement specification. So here we can't see the actual requirement specification. We're just seeing an example of what it looks like to record these responsibilities. So this is actually one of the first design tools, right? The idea of these class cards. And the class cards, there's one class card for every class you identified. It identifies its superclasses and its subclasses and its responsibilities, right? This 5 by 7 is very old. It refers to 5 inches by 7 inches, right? That's kind of an index card. If index cards still exist, hopefully they do. Okay, I'm going to wrap it up there. Are there any questions about objects and responsibilities? So you will get you will see some of this stuff in action as we go along. And next week, I think you're going to get the coursework. So you'll see what it's like to get a coursework, and then you can start applying these principles in your coursework. I'm not going to give away the details of the coursework. I'm just going to say we're hoping to hand it out next week. And you're given a system, and then you're asked to modify the system to fix things that are broken or are not very well designed, and add new functionality where it's specified. So it's not very difficult to imagine, actually. So you'll have 1 hour to complete the coursework. No. The coursework will be due in December, actually. But I've seen an initial draft of the coursework. The recommended time to spend on the coursework is 70 hours. So it's sort of 70 hours, I would say, spread over roughly 4 to 5 weeks. It's definitely not something that you'd want to wait for until the last day or so. It's definitely something you'd want to set aside, for example, 1 to 2 days a week to work on. Actually, it might be more than that. It might be something like 3 days a week. You'd have to figure out 70 divided by 5, which is like something like 13-ish, 12 to 13. So you'd want to set aside something like 12 to 13 hours per week to work on it, which is, I guess that's about 2 days a week, approximately. Yeah. Any other questions? Okay, thanks everybody for joining the class today, and I hope you found it educational. And I look forward to seeing everybody next time. If you do have questions, write them down and ask them during the next lecture. That would be really great. Have a good weekend.